Today's topic is two more special cases. 6.5 special case. So in this case, we will see that Q binomial coefficients appear. So we first need to define something. Yeah. So definition. So there's a area in mathematics called a Q series where people study things related to generating functions in Q. Then there are quite useful area in number theory and also in combinatorics and orthogonal polynomials. I'm not sure I can cover this, but if you have time at the end, I'll tell you some things about orthogonal polynomials with Q. And but for now, Q is just a parameter, just like X. But for some reason, people use Q as a variable. Let me just tell you basic definitions. So for an integer, non-negative integer n, the Q integer which I denote bracket n sub q. The Q integer is defined to be equal to 1 minus q to the n over 1 minus q. But if you can factor this out, the numerator, if you factor this, and it's actually a polynomial, so 1 plus q plus dot 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 q to the n minus 1. Okay, so if q equals 1, or q approaches 1, if you want to take this as a definition, then this is just n. So you can think of this as a kind of generalization of the integer n. Okay, so we have a parameter, and the q factorial which I denote by n sub q factorial, like this. Okay. Definition: 1q, 2q, like n factorial with the q integers. Okay, quite simple. And the q binomial coefficient which we denote bracket with nk, n up at the top, k at the bottom, with sub q. And this is defined just like the binomial coefficient with q factorial, like this. N minus k q factorial. Okay. So again, if q equals 1, we see that this factorial, q factorial is just n factorial, and the q binomial coefficient is the usual binomial coefficient. Okay. So and it is not obvious, not completely obvious from this definition, but this is also a polynomial in Q. So we will prove that. So for, by the way, of course, here, k greater than or equal to 0, less than or equal to n. So if k is greater than n, we define this to be just 0. Okay, and lemma. So but let me just recall you the Pascal's identity. What is the Pascal's identity for binomial coefficient? Pascal's identity says n choose k equals n minus 1 choose k, n minus 1 choose k minus 1, right? It's a simple binomial identity. And we have a lemma, which is basically a Q Pascal identity. Pascal identity for Q binomial. It's slightly different. It's quite similar, but slightly different. Q to the n minus k, n minus 1, k minus 1, n minus 1, k. So if q equals 1, this disappears, so it's exactly like this, but we have some vector like this when q is non-zero. All right, proof. Just like Pascal's identity, using just this definition, this is just immediate, just a computation. Okay, yeah, let's do it. Anyway, so n factorial, k q factorial, n minus k factorial. This is the left-hand side. And we're gonna right-hand side. We will rewrite the right-hand side so that this becomes this. Okay, so proof is really simple in that way. Q to the n minus k, n minus 1 q. Let's omit sub q. Sometimes people do that, and we can do that too. N minus k plus n minus 1 factorial, k factorial, n minus 1 minus k factorial, q factorial, okay? Now we can factor, or we can combine the denominator. Let's say k factorial, n minus k factorial. And q, the first, if you look at the first one, originally we had this, but we multiplied a k here, right? If you multiply k here, this becomes this. So we have to multiply k above 2. Just k, not factorial. And also here, n minus 1 factorial. And we multiplied n minus k here to make this. So it's going to be n minus k. But now we can factor this k factorial, n minus k factorial, n minus k factorial, n minus 1 factorial. And now let's see what's the remaining thing. So we want this to be equal to n, but because that will give us exactly this. But if you think about the definition, this one, then this is like 1 plus q plus dot 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 q to the n minus k minus 1. But this, initially we have 1 plus q plus dot dot dot, but because we multiply this will be exactly the one after this. So this becomes this. So that's the proof, basically. So this is n. So that's the proof. Yeah, that's the computation. So nothing difficult. And these binomial coefficients are related to lattice path, and Q binomial coefficients also they are related to lattice path, and also they are closely related to what's called partition. So let me define a partition. It's a very elementary and useful definition. So you can see this many different different places in mathematics. A partition is a sequence. So we usually write a lambda 1 dot dot dot, a lambda say k. Unless it's L, it doesn't really matter. But it's unfortunate that we use lambda n for our recurrence coefficient. But yeah, I will use this here as well. It's a sequence of integers such that lambda 1 weakly decreasing. They are non-negative like this. Sometimes people only consider positive things, but we're going to use the non-negative 0 as well. So partition is just this, and each lambda I is called a part. Okay. And the size usually denoted by this absolute value sign is just sum of all the entries there. Okay. And the Young diagram for partition is just this. We draw boxes like this, something like that, where here first row is lambda 1 boxes, lambda 2 boxes, etc. So for example, if lambda equals 4, 3, 1, then this Young diagram is 1, 2, 3, 4, like that. Okay, so we can visualize a partition like this. And oftentimes we just ignore zeros. So zero, whenever you add zeros or delete zeros, they all considered to be the same partition. So yeah, they are the same. So they don't appear in the Young diagram. Okay, and the transpose of lambda is denoted by lambda prime, but this is the partition whose Young diagram is just a Young diagram of is the Young diagram of lambda are transposed, reflected. Let me write it more clearly. The main diagonal. So, for example, if lambda is 4, 3, 1, or is lambda prime, you just flip this along the main diagonal, then you get something like this: 3, 2, 2, and 1. So lambda prime will be 3, 2, 2, 1. Okay, so quite simple. And also some for notation, A to the B means A dot 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 with BAs. Just for shorthand, this is a shorthand for this sequence or partition. This is a rectangle. It's like this is A and this is B. Okay. It's a rectangle. Oh yeah, and one more. We write for two partitions, mu and lambda, if the Young diagram of mu is contained in the Young diagram of lambda. For example, this is contained in the I think it's too general and it looks too special. So let me write something that doesn't look special. 4, 3, 1. It contains the 2, 2 is contained in 4, 3, 1. Okay. like that. All right. By the way, from this, actually, from this recurrence, this is a recurrence, by the way. You can compute this using something with a smaller n. So you can compute this using this recurrence. Then from this, you can actually prove that this is always a polynomial. But we will give a proof of that polynomiality in a more transparent way. So proposition for integers k and n, we have combinatorial interpretation for the Q binomial coefficient. This is the sum over all partitions contained in, let's say, n minus k to the k, q to the k, lambda. So this means that lambda is contained in this box. Lambda is somewhere like this. And you add a number of boxes here and raise it q to the number of boxes there. Then you add this for every lambda, then you will get this. So if you can prove this, then it's clear from this that this is a polynomial in Q, right? And also the coefficients are non-negative integers. The proof is basically induction, simple induction. If you can prove that, so we know that this satisfies a simple recurrence. If we can show that this also satisfies the same recurrence, then we are done. So, okay. Let's see, induction. Okay, if n equals 0, the base case, then k must also be 0 because k is between 0 and 1. And this is true. Here is like lambda is empty. It's contained in the empty, so by definition is like due to the empty. So this is true. This is okay. So suppose that, and suppose the statement holds for n minus 1, and then we're going to prove our recurrence. And okay, let's say maybe L, R for right hand side, be the right hand side. I mean this, and we will show so enough to show that the right hand side satisfies the same recurrence. So what was the recurrence? R of n comma k equals R of n minus 1 k plus R of n minus 1 k minus 1, but here we put q to the n minus k. That was exactly the recurrence for the left hand side, like this. Okay, so it's enough, because then by induction this is going to be n minus 1k, this will be n minus 1k minus 1, but then this whole thing is n choose k by the identity of the Pascal identity for q binomial coefficient. So our goal is to prove this, but this should be quite easy to prove now, because if you think about the diagram of the of lambda contained in this box, so R and k is the generating function for all this k, right? And we add for each lambda, we add q to the size of lambda, meaning the number of boxes inside this lambda. So there are two cases here, and this can also be considered as like lattice path from here to here, right? Because the border of the lattice path, determines the border of the partition of the Young diagram, so it's basically the same. So there are two cases. So case 1. So here we go say this way in the lattice path. Case 2, we go in this way first. Took this step first. So this means lambda 1 is n minus k. The Young diagram contains the full row. The first row contains the full row. So case 2 means that lambda 1 is less than n minus k, basically. But in this case, this lambda 1 is decided. Now you have to find partition here except the first row. That is exactly R of n minus 1, k minus 1, as k. Yeah, this is n minus 1 minus k minus 1, so that's this. Is that right? No. K minus 1. Okay. Yeah. Oh, yeah, I think that's right. Yeah, I don't have to match the same thing. The match is this way, unfortunately, but that's okay. But is that right? It's possible. Yeah, the recurrence is false. Let's see. It's possible that I made a mistake, but this proof looked okay, right? Where was the mistake? Okay, let's do this. We just continue this proof and then find the error there. It looks like this is okay. And here we go this way, and then so we can just ignore this last column. So this is n minus k minus 1, and this is still k. So it's going to be r n minus 1k. So this is q to the... Actually, because of this, we have to multiply n minus k. Here is this. So I think the recurrence should be this. That means we have to put this over here. Oh no, that's exactly this. I see. I think, yeah. This was the mistake. Right? Okay, yeah. Yeah, it's correct. Even in the order is correct. That's the proof, okay? So this is probably the simplest combinatorial interpretation for this. This is the basic combinatorial interpretation of the Q binomial coefficient. Either you can think of this as a generating function for partition inside this, or you can think of this as a lattice path, generating function for lattice path with areas here, counting the area of this. And of course, obviously, if you take the transpose, it doesn't really matter if you consider lambda here or lambda contained in its transpose. So this also true corollary is that nk is the generating function for lambda contained in... We can either put this, or taking its transpose, they are the same. Because here we consider m minus k lambda here. But if you take the transpose, k and n minus k, right? So lambda is here. So you can choose this or this, anything that you want. But actually there is also a similar recurrence where this goes over there. But then you will put q to the k. But proof is really the same. Okay, now let's see. Right, now we can now go back to the special case of the b's and lambdas. If bk equals q to the k and lambda k equals 0, then mu nk equals nk, and nu nk is this. So these two as matrices they are inverses of each other. Okay, so proof. But in fact, this can be proved quite easily because let me recall you the general special case. Yeah, this one. So if bk is arbitrary and lambda equals 0, then nu is the homogeneous symmetric function, and nu is with some minus sign, elementary symmetric function. We will use this. Since so mu n, okay, maybe just we know we have, let's say we have mu n k h n minus k. Here we x0 x1 dot 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 x what was it, xk, where xi equals q to the I, because we consider the general case, but xk is q to the k. Okay, and maybe I can nu nk minus 1 to the n minus k is the n minus k, x0 dot 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 up to xn minus 1. This is the theorem that we proved before. Then we just specialize this xi to the q to the I. Okay, maybe I can continue here. So, but what is this? What is mu nk? If you plug in xi equals q to the I, this is going to be a sum over, by definition of the homogeneous symmetric function, it is 0 I1 in minus k up to k, right? And here we multiply xi1, xi2 dot dot dot, but xi equals q to the I, so they are just q to the I1 plus dot 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 I n minus k. Okay, but what is this? Increasing, or if you read this way as a partition, if you read backward, the weakly decreasing sequence is a partition. So we can rewrite this in the following way. Sum over this lambda 1. If you think about lambda 1, lambda equals I n minus k dot 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 I1, this is a partition contained in where the maximum size is k, so k to the number of parts n minus k. Okay, so this is equal to sum over lambda contained in k to the n minus k q to the, but this is exactly the size of lambda, right? But then this we have this theorem over here, or this is n choose k. This is done. And what about the nu? The similar is by definition of the elementary symmetric function n minus k. Let me compute this minus 1. Let's get rid of the sign and then see what happens. This is sum over 0, I1. Now they are all distinct. I n minus k. The largest possible one is n minus 1. And q to the I1 plus dot 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 I n minus k. But this is not exactly this, but because of this condition, they are all distinct. They are all, if you read this way, so lambda, if you define lambda equals I n minus k dot 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 I1, this is a partition, but this is always strictly decreasing. Okay, but where is this contained? This is contained in the maximum possible number is n minus 1, and we have n minus k things like that. Then let's draw the diagram. N minus k, n minus 1 here, n minus k here. Maybe I can make it a little larger. There are still a path from here to there, but you have to always go up like this. I mean, you cannot go up, because then these have two equal parts, right? So how can we deal with this? But if you think about it, this will always, a common trick here is you just subtract some numbers so that we have weakly decreasing sequence. So define, say, mu is lambda minus, the first, you subtract the 0 at the end, 1, the second to the last, dot dot dot, so n minus k minus 1. You subtract this from that. That means we subtract things like this. We subtract this, and then just look at these numbers. This is mu. Okay? But then this can be considered as, I think I don't have enough space, so let me just move this to the next slide. So originally, we have this. We subtract this, then the red things, we still have the same number of rows, but this is n minus k minus 1. We subtract from there, so it's going to be n minus 1 minus n minus k minus 1, which is what? K. So this is k. So this is k. So you go from here, something like that. So now you don't have any restriction. You can go something like that. It's okay. They are in one-to-one correspondence. But if you have lambda here and mu, what is their what is the relation between their sizes? We subtracted this from lambda, right? So lambda is bigger. Then the amount that how much lambda is bigger is this. So it's going to be 0 plus 1 plus dot 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 n minus k minus 1, which is exactly n minus k choose 2. That this is equal to this, right? So this equals sum over lambda, in summary, strict partition, let's say, strictly decreasing. But this is equal to, if you consider this correspondence, you just get rid of this and then just consider this part. This is sum over all mu, k to the n minus k, q to the n minus k choose 2 times q to the mu, like that. this is what? Q to the, and this, it doesn't, is a constant, and choose K. And that's why this is equal to this times this. So that's the proof, that's the proof. All right, so yeah, in this case we have Q binomial coefficients, and it's dual in the sense so that the inverse of the matrix is this. Okay, and we will see one more special case. Special case. Stirling numbers. Stirling numbers. So we will consider this case, bk equals k, lambda equals lambda k equals 0. Okay. And the theorem is, let me just write down the theorem. If this, then mu and k is the Stirling number of the first kind, and nu and k is a Stirling number of the second kind. We have sign here, if you remember. This is always non-negative, and this has plus or minus sign. And we actually know that this and this, they are inverses of each other. The matrices are inverses of each other. But we can also see this from this fact. So let's prove this. Proof. And here we will let's recall if bk equals k plus 1, lambda k equals k, then we know we have this Charlier histories. Like mu, in this case, mu and k equals sum over all, let's say, row Charlier histories, nk. Oh, okay. Let me just use this just n case. So ignore k here. Yes. By the way, the notation is not very good. Yeah, I'm using k everywhere. Let's say r. And if this is r, this is r. This is, actually, basically just a number of Charlier histories. Remember Charlier history? We have up, horizontal, or down, something like that. Here, the usual weight is B2 in this case, but this is 2 plus 1. That means we select here, we label this 1, 0, 1, 0, 1, 2, among 0, 1, 2. We put weight here. And here is the lambda 2 equals 2, then we label this with 1 or 2, like that. And yeah, that was the definition of a Charlier history. And then we know that this corresponds to set partition, if you remember. So set partition, like something like that. Set partition. We may have some singleton blocks and things like that. Okay, that was something that we saw before. But in this case, in our example, in our case, lambda equals 0, and this is r. Then, but we can still think of this as a Charlier history with some a truncated Charlier history. We have at the end, we just get rid of the part. So if BR equals R, lambda R equals 0, then mu and K equals the number of Charlier histories from the Mochkin path is from 0, 0 to n, k. But lambda is 0. That means we cannot have any down steps with only up and horizontal, no down. And every horizontal, like this, if the height is I, we have choices, label. Before we have label 0 up to R in this case, but we just we have one less than that, so let's label in 1 up to I, let's say. So we have maybe I can give you an example, something like this. Let me just move this a little up, horizontal, up, horizontal, up, horizontal. So this level 0, 1, 2, 3. So here we have a level 1, so actually we have only one choice for there. We don't have any horizontal steps at the bottom because we cannot label it. The only possible is label 0, but we don't allow 0 there. And here is a 0 or 2, but 1 or 2, but let's say label it 2, and this is 1, 3. So this is an example of Charlier history, a part of the Charlier history. Okay. Now we do exactly the same thing with a set partition bijection. Okay, so it's 1, 2, 3, 4, 5, 6, 7, and 8. So we're gonna connect them. So up step means opener. Up step means opener. Horizontal step means transient. So it goes something like this. But sometimes we may have like a singleton like this, but we don't allow that because 0 is not there. So horizontal is always like this. Horizontal always looks like this. Up step always looks like this. Up, horizontal, like that. Okay? And we are gonna connect this using the labels here. Connect with the first available opener or available open arcs, like this. 1, 1, and here 2, first, second, so we connect with this. Okay, but yeah, it doesn't really matter, but I'm gonna connect starting from the closest one, so first and second. Okay, and here first, and here 1, 2, 3, so it's connect something like this. So at the end we have a configuration like this. But what you can notice here, every block, every connected component looks like every block is of this form. And then unfinish it. Because if you want to finish it, we need a down step. We have a down step, then we can finish it. But we cannot finish it. But because there's no label 0, we cannot have a singleton as well. Okay? But this is fine. This is fine. But yeah. For instance, if we had this, then we would have, maybe I think we can. If we had this, then we would have something like this. So everything looks like this. But how many blocks, unfinished, incomplete blocks are there? Whenever we have an up step, we get one block, a new block, and it will not be finished. So the number of blocks will be exactly the height of the ending height. But this is the number of the of steps. This is k, right? Ending height is k. So basically, just imagine that this is once. Just ignore this the thing at the end. And we get just a partition of Z partition of n with exactly k parts. So number of such Charlier histories equals number of set partitions of n into k blocks. This is exactly S of nk by definition. So that proves the first statement. Where is it? This. What about the second? The second statement, we will use the known fact. For the second, okay, right. Since PR equals R, lambda R is always 0. Let's just compute the Pn, the orthogonal polynomial Pn, or just a polynomial with a three-term satisfying the three-term recurrence. Then, if you remember three-term recurrence, it looks like this. But lambda is 0, so you can just forget about this. That means you just keep multiplying x minus Pn. So this will be. This is by definition k from 0 to n, nu and k. The coefficient of the polynomial, it was the coefficient of the polynomial. This is like you just stack x minus b0, x minus b1, x minus b n minus 1, which is in our case x minus 1 dot 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 x minus b n minus 1 or n plus 1. Yeah. But we know that this is the generating function for the Stirling number, x to the k. And because if you compare this, nu and k equals s and k. The reason why this is because we know that sum over all permutations of Sn, x to the number of cycles of x, of pi, we show that this is this. So if you replace like pi and actually this is like signless Stirling number of the second kind. And if you replace x by minus x, and if you multiply both sides by minus 1 to the end, then we know that this is equivalent to this. So that's why it's true. So but anyway, so we have identity like this. That's the proof of the proposition. So in summary, if we have this substitution, we get on one side as a mixed moment, we get the Stirling number of the second kind, and then the coefficient side we get the Stirling number of the first kind. So we have the duality. So we saw 4 special cases of the duality between the mixed moments and coefficient, and then we got many well-known dualities. Okay, that's it for the chapter 6, and I think I can say a little bit about chapter 7. Just a little bit. So chapter 7 is about determinants of moments. But let me give you the motivation. And maybe, just the first section, computing Bn lambda n using mu n. So recall, we can compute mu n using a bn and lambda n, like a pi in the Mochkin path, weight of pi, where the weights are decided by these b's and lambdas. That means mu has a formula in terms of b's and lambdas. But can we do the opposite? Can we find bn and lambda n using mu n only? The opposite thing. But actually the answer should be yes, because mu n, this completely determines the linear functional. That means it determines the polynomials. So they determine the polynomials, so of course determine the recurrence coefficient. So in theory, this will determine bn and lambda n. But the question is, how can we compute? How can you find the formula? Can you find an explicit formula for bn and lambda n using mu n? But before doing the general theory, let me just convince you there is a way to compute bn lambda n using only this formula. Okay? Answer is yes, like I said. But we will consider just a small case. For n equals, say, 1, 2, 3, if you compute this formula, what is mu 1? There is only one lattice path, Mochkin path of level of length 1, has weight b0, so this is b0. And what is mu 2? We have either this or this, so sum is like b0 squared plus lambda 1. And lambda mu 3, we have this or this. I think that's all. So it's like b0 cubed, 3b, oh no, not 3. 2b0, because b0, b0, but this is b1. Lambda 1, p1, lambda 1. We have things like this. But even with this, we can compute the first few b's and lambdas. Actually, from this, we can immediately see that b0 equals lambda 1. What about lambda 1? Now we know that this is, mu 1. Now we know this is mu. We express everything except lambda 1 using mu. So we can write lambda 1. And lambda 1 is mu 2 minus b0 squared, but this is mu 2 minus mu 1 squared. Everything in terms of mu. And finally, here, we know this and this and this, so we can compute b1. Lambda 1. Lambda is non-zero, if you remember. Is that right? Yeah. And yeah, so if you write lambda 1 equals mu 2 minus mu 1 squared, mu 3 minus this is mu 1 cubed minus 2 mu 1. It's complicated, but everything is in terms of mu. You may now be convinced that if you do this over and over, then we should be able to find all the b's and lambdas. But actually, we can actually prove it. We can actually prove that it's possible. So this is always possible. Because if, let's say b0, we computed b0, bn minus 1, lambda 1 up to lambda n. These are known. By known, I mean they have formulas in terms of mu's. Then we can also find a formula for bn, because what is mu n. What is mu n? Sorry, not mu n, but mu 2n plus 1. Let's consider mu 2n plus 1. Then there will be many things, but Bn appears only once. Bn only appears once, like Bn. This is the only possibility that Bn can appear. And then like a lower terms, let's say, lower terms. Lower terms are known because of the assumption. And this is lambda n, lambda 1. So they are all also lower terms. That means Bn like in terms of mu's, mu i's. Okay? By induction. And also if B0, Bn, and lambda 1, lambda n are known, then we consider we want to increase this index by 1, like we want to compute this. But so we consider mu 2n plus 2. Then lambda n plus 1 only appears once over here. Here is a n plus 1, n plus 1. So here the first up step is, down step is n plus 1, lambda n, lambda 1, and then again lower terms. Right? That means we can also find lambda n plus 1 using in terms of mu i's. So in this way, of course, it will get very complicated, but we can always compute it. We can program it actually to get a formula for mu's and lambdas using only this thing. Okay, so if you can write some mathematics program, then you can do this. But of course, this is not an explicit formula. We only know some kind of algorithm to decide to compute mu n. So the question is explicit formula. Is there an explicit formula for b's and lambdas in terms of mu? And that's the goal of this chapter. And we will we will actually study some very interesting theory in what's called non-intersecting lattice path. And answer is again yes, but we will use. We need to build some theory. Very interesting theory on non-intersecting lattice path. So that means basically means you have some bunch of paths with starting and ending points fixed, but they are non-intersecting like that. And there's a famous lemma called Lindstrom Gesell-Vienno lemma. This tells us some kind of determinant equals the generating function for all non-intersecting lattice path. This is a very useful and elegant theorem or lemma. So if you know, there's a book called Proofs from the Book. From the book. There is a book called, title is Proofs from the Book. So the story is like, you know, Paul Erdős. Do you know the mathematician Paul Erdős? He was a very famous mathematician, and he, of course, loved the math. And then he used to say that when he was alive, he used to say that there is a book in the heaven. There is a book in the heaven, and that has the most elegant proofs of all the mathematical theorems. So we as mathematicians, our duty is to find the proof from the books. Okay. Yeah, but actually there was a funny cartoon that I found somewhere in the internet that eventually when Erdős passed away, the cartoon drew Erdős in the heaven, and he finally found the book. And the book, in the first page of the book, says theorem, Riemann conjecture is true, and then proof, trivial. So maybe he was disappointed, but actually it's true because there are only two things in mathematics: unsolved problems, and a trivial statement. So if you prove something, that becomes trivial, in some sense. But anyway, the point here is that this book is of course not really the book in the heaven, but two mathematicians wrote this book, and they collected what they believe that all the beautiful and elegant proofs that have been discovered in the real life. And the thing is, there are many things, and this is one of them. So Lindström-Gesell-Vienna lemma is a beautiful theorem. If you understand, you will see the beauty there. So you can also find it in the book, proofs from the book. And the theorem itself is quite elegant, and proof is also beautiful, but more interestingly, it's very useful. So if you will see, if you study algebraic combinatorics and enumerative combinatorics, you will see this all the time. So very useful and beautiful theorem. So we will do this the next time.